Hi, welcome to a new session of Circuits and Networks. In today's class 3, under filters, we are going to see m-derived low-pass filter and the problems which are associated with m-derived low-pass filter. So you can see a rough figure in figure 1 and figure 2, how m-derived low-pass filter look alike. The left side is the T section and the right side is the pi section. So how to design these kind of filters? So this is our interest. So we'll start with the basics what we have learned in our last class. So for a K-type low-pass filter, T section you can see L by 2 is the arm shared by C under T section, whereas on the pi section you can see C by 2 is shared in series with L. So this is the design of low-pass filter of K-type. So the basic formulas for this low-pass filter, we have the characteristic impedance K given by under root L by C, which is equation 1, and the frequency it is obtained to be 1 by pi under root LC. Then the formula for L and C can be derived from equation 1 and 2 as 3 and 4. So this we have learned in our last class. So from K-type low pass filter under T section, the disadvantage is the attenuation, means the unwanted signal is not sharp in the stop band, and the characteristic impedance, that is K, varies widely in the pass band. So this is the main disadvantage of K-type filters, whether it is T section or pi section. Anyhow, the modified K-type, or you can say the m-derived low-pass filter, you can see the arms L by 2 are as it is, and C it is also as it is, but here we have introduced another inductor. So since we have designed this as m-derived, so we have the input and output, and the impedance you can see we have taken here as m L by 2, and the resultant of the division is obtained to be 1 minus m square by 4m and mc. How we got this, we are going to see now. So first we take the basic K-type low-pass filter T section, where we have Z1 by 2, Z1 by 2 and Z2. It is a basic K-type low-pass filter under T section. Now if at all I want to change it to m-derived low-pass filter, then it will be mz1 by 2, mz1 by 2, where m is the derivation what we have to derive, and this leg which is shared by these two arms is treated as z2 dash. So how to derive this z2 dash, we are going to see now. So for a constant K T section, ZOT, that is the impedance of the T network, is given by under root Z1 square by 4 plus Z1 Z2. Similarly, on the basis of ZOT, on the m-derived filter T section, I am going to get ZOT is equal to, I have mz1, so that it becomes under root of m square z1 square by 4 plus mz1 z2 dash. It's an open circuit impedance. You have to treat the output leg as open circuit, then you are going to get the total impedance of these two sections. Now these two, that is the K type and m-derived type, you can see the characteristic impedance is almost similar. So what we are going to do, we are going to equate these two impedances. So when you are going to equate these two impedances on the right hand side of the above two formulas, we are going to get under root of z1 square by 4 plus z1 z2, which is matched with under root of m square z1 square by 4 plus m z1 z2 dash. So easily we can get the value of z2 dash, which is equal to z1 of 1 minus m square by 4m plus z2 by m. So hence in figure 2, z2 dash can be replaced by this particular formula. So z2 dash must be an impedance composed of two series impedances, that is z1 of 1 minus m square by 4m and z2 by m, where m range should be between 0 and 1. So it's a minute change, that's why it should be in the this limit value. So you can see this m-derived low pass filter is framed as new one in this form, that is modified m-derived low pass filter under T section. Right. Now what is this Z1 and Z2? Generally Z1 and Z2 we take the impedance value as inductor and capacitor. So let us take the value of Z1 as j omega L and Z2 as 1 by j omega C. Now these two we have to substitute in the formula to get the values of the center limb, that is the Z2 dash value in this form. For that, we have to keep in our mind that at a particular frequency, the shunt arm of T section will be in resonance, giving a short circuit to the input, causing an infinite attenuation. Means what? We have to take the resonant frequency condition. Under resonance, we know that XL is equal to XC, or the voltage drop across inductor is equal to the voltage drop across capacitor at the central limb. At the central limb, we have taken the value of Z1 and Z2 as omega L and omega C. So omega L is equal to 1 by omega C at resonance, and we are taking at the resonance condition. That's why we are replacing omega by omega naught, and we have taken the values of arm as 1 minus m square by 4m on the left side. On the right side, we have taken the value as 1 by m omega naught C. So you have to take omega naught into the account. So omega naught is obtained to be 2 by under root of 1 minus m square LC, where the angular frequency can be changed to the natural frequency f naught, which is equal to 1 by pi under root of 1 minus m square times LC. Now f naught is here treated as f infinity. Here we are defining f infinity as the attenuation frequency. What we know that fc is equal to 1 by pi under root LC for low pass filter, right? So we substitute this equation 1 in this formula, and we are going to get the attenuation frequency formula, which is equal to fc by under root of 1 minus m square. And hence we can derive the formula for m, which is equal to under root of 1 minus fc by f infinity, or attenuation frequency square. So this we are treating as equation 6. So anyhow, rearranging the concept of K type low pass filter pi section, we are going to get the same thing, that is the arm which is in series, which is shared here for the parallel legs, that is ml, and that is 1 minus m square by 4m multiplied with c. This is the resultant of pi section. So what we have to know, at a particular frequency, the shunt arm of the T section or series arm of the pi section will be in resonance, giving short circuit to the input for T section and open circuit for the pi section, causing infinite attenuation. And that is what we have already found out. So you can see here the T section and the pi section of m-derived low pass filter, the basic diagram. Now what we need to keep in our mind, the formulas. What are the formulas? The formula for the cutoff frequency, that is 1 by pi under root LC. The actual formula for low pass filter for designing the inductor and the capacitor, given by equation 2 and 3. And the recent formula, that is the attenuation frequency in terms of cutoff frequency, and the formula for m, which is in terms of cutoff frequency and attenuation frequency. These we have reframed the new equations, and we are going to follow these new equations to design m-derived low pass filter. So we'll go with the first problem. We have to design an m-derived T section low pass filter having cutoff frequency as 700 Hz with design impedance of 400 ohms, and the frequency of attenuation is 900 Hz. So you take the data as it is, that is K, Fc and F infinity. And for the low pass filter, remember the formula of L and C. Just we are going to replace the formulas with the actual values given in the data. So we are going to get the value of L and C, which is 182 millihenries, and C value is 1.137 microfarads. Fine. Now for m-derived low pass filter under T section, we have derived the formula for m, which is under root of 1 minus Fc by F attenuation, that is square terms, and we are going to apply the values of Fc and F infinity, and the value of m is obtained to be 0.63. But what is the requirement? We require the value to be ml by 2 and the arm, that is the series arm under T section. So for that we are calculating the ml by 2 value, which is 57.33 millihenries, and the MC value is obtained to be 0.716 microfarads, and the value of the inductor, which is the part of Z2 dash, it is obtained to be 43.55 millihenries. So this, you can see the values are substituted over the m-derived low pass filter. Now this actual formula can be replaced by the original circuit with ml by 2. The formula, the value of the formula is changed to be 57.33 millihenries on the both sides, and the new value of the MC is 0.716 microfarad, and the value of this 1 minus m square by 4m multiplied with L is obtained to be 43.55 millihenries. So this is a m-derived low pass filter under a T section. Now what is going to will be our interest is to concentrate on the pi section. So for the pi section, the values of the given data of K, Fc and F infinity are given as 500 ohms, 800 hertz and 1000 hertz respectively. We know that the formula for L and C, we'll substitute the values of L and C. We got the value of L and C in the numerical values, which is shown over here. And we know that the pi section m-derived filter looks like this. And for this T section, we can frame the formula for M, and it is obtained to be 0.6. Let us substitute these values for MC by 2 and ML, and then 1 minus m square by 4m multiplied with the C. We got this value as 0.213 microfarads. Just replace this figure 2a m-derived low pass filter pi section with the original values what we have calculated just now. So you can see the arm is shown in this fashion with the MC by 2 followed by 0.24 microfarads. Then you have the series arm shaded by this parallel, which is given by these two values, and hence this is the design of m-derived low pass filter under pi section. Now try to solve the same concept with question 3, 4 and 5, and comment in the chat box whether you are able to design the low pass filter under T section and pi section for m-derived case as well as for k-type case. So that's all for today's class. I hope you like this particular video. Please share among your friends, subscribe to this channel and press the bell icon for the future notifications. Thank you.